Okay, in this video I'm going to talk about cyclic quadrilaterals or inscribed quadrilaterals. It's the same thing. So basically cyclic quadrilateral is a quadrilateral that whose vertices lie on a circle. So for which there exists a circle passing through all four vertices of this quadrilateral. So something like this. So let's write it as a definition. So a quadrilateral is cyclic if there exists a circle passing through all four vertices of the quadrilateral. So there are several criteria how to establish if a quadrilateral is cyclic. So the first one is that the sum of the opposite angles in the quadrilaterals is equal to 180 degrees. So let's write it as a theorem. So a quadrilateral is cyclic if and only if, so it holds in both directions. If and only if the sum of the opposite angles, the sum of its opposite angles, let's write it this way, of its opposite angles is equal to 180 degrees. So okay, so let's prove it. So basically it's easier to prove like in this direction. So if we assume that it is cyclic, so we assume that it is cyclic, so then we have a circle and all the vertices lie on this circle. Something like this. So then we notice that what is the sum of the opposite angles. So this angle, so let's denote the vertices A, B, C, D. So we notice that the angle A is equal to 1/2, so it subtends the arc BD, right? It subtends this arc BD, therefore it's equal to half of this arc BD, because it's an inscribed angle. Any angle that is inscribed in a circle, it always equal to half of the arc which it subtends. So, and similarly, the angle C is equal to half of the arc BD, and yeah, it's actually, in this case we need to write the arc in 3 letters, because to know in which direction it goes. So because arc BD, there is this arc BD and there is this arc BD, small and large. So this is the arc BCD, and here would be the arc BAD. Right, so but we notice that these two arcs, they when we bring them together, they form the full circle. So these are the two, the sum of these two arcs is 360 degrees. So from this we conclude that the sum of the angle A plus the angle C is equal to 1/2 of the, well, we can rewrite it, the arc BCD plus the arc BAD, and this is equal, so this is the sum of, let's write this more carefully, BCD plus the arc BAD. And so so BCD plus the arc BAD, that would be the full circle. So 1/2 of 360 degrees, which is equal to 180 degrees. And that concludes the proof, only in this direction. So now let's prove it in the let's prove the converse statement. So now we assume that the sum of, assume that the sum of angle A plus the sum of the plus angle C is equal to 180 degrees, and we need to prove that the quadrilateral is cyclic. So we have a quadrilateral, let's say something like this, and we know that the sum of these angles is equal to 180 degrees. So what we can do basically is let's draw a circle through the circumcircle of the triangle BCD. So let's consider the circumcircle consider the circumcircle of the triangle BCD, right? So it would be a circle passing through B, C, and D. Let's say that it doesn't pass through A. If it passes through A, then we are done. So let's say that it doesn't pass through A, then we consider the second intersection point of this circle with the line AD. Right, so let's denote this point by A prime. Right. So then the triangle, the quadrilateral, so then the quadrilateral A prime BCD is cyclic, right? Because by construction, like all four of its vertices lie on the same circle, right? So then it is cyclic, and using the part of the statement like in the opposite direction that we already proved, right? What we previously proved, we conclude that the sum of its angles of this quadrilateral is 180 degrees. So the angle, basically the angle B A prime B A prime D plus the angle C is equal to 100 degrees. So this angle plus this angle. But then since we have this and since we have this, we subtract one from another and we conclude that the angle A, or like the angle A, yeah, it's this one, so BAD is equal to the angle BA prime D. So BAD is equal to BA prime D, right? So, but this is impossible, of course. Well, like the equality of these angles, it implies that that BA, so it implies that one way to prove it is that BA would be parallel to BA prime, and then since these two lines have point B in common, then they must coincide. It must be the same line. Or another way to prove it is that A prime, like BA prime D, is an external angle in the triangle BA prime, right? External angle must be equal to the sum of the two other angles, so it would be angle A plus angle B plus this one. But since these two are equal, then the angle B, like A prime, would be 0. So this would be 0. So, but like anyway you prove it, the conclusion is that so from this we conclude that BA is the same line as BA prime, and from this we conclude that A is equal to A prime. A and A prime is the same point. And then so from this finally we conclude that it is cyclic. So from this we conclude that ABCD is cyclic, because A prime BCD is cyclic and A is the same as A prime, so ABCD is the same as A prime BCD, and then it is cyclic. So this concludes the proof of this direction in the theorem and the whole theorem as well. So now there are different there is a different form of the same criterion of cyclic quadrilateral, and it can be stated as this way. So a quadrilateral is cyclic if and only if one of its angles is equal to the opposite external angle. External angle. And so to draw this, if this is a quadrilateral, then basically this angle is equal to external angle at the opposite vertex. This is just a simple corollary of the previous theorem, because let's write more carefully the word external. So that it would be readable. External. This is a simple corollary because the external angle, of course, is, so like if we denote this by alpha, then this angle would be 180 degrees minus alpha, right? So, and basically the condition that the sum of the angle let's put it A and C, right? So the condition that the angle A plus angle C is equal to 180 degrees from the previous theorem is exactly the condition that because the angle C is equal to 180 degrees minus the external angle C. Like if you denote like some point P here, this would be 180 minus the angle BCP, right? So, and this condition transforms to angle A would be, because 180 degrees cancels, would be equal to the angle BCP. So the angle A would be equal to the external angle. Yeah, so this is a simple corollary of the previous theorem, and then there is another criterion. Again, a quadrilateral is cyclic if and only if. So here it would be more convenient to write, like to denote already for the statement of the theorem, to denote the vertices of the quadrilateral. So we consider the diagonals. So if these angles are equal, so if the angle ABD is equal to the angle ACD. And because of the like symmetry of the letters, like it would be the same as the angles between the other diagonals, we can write, for example, that these angles are equal. Like it would be the same criterion. Or let's say these angles are equal. So the point is that it's the angles between sides and diagonals that kind of look at the same side of the quadrilateral. So look, subtend, like I'm not sure if you can use the word subtend for a side of quadrilateral. It's usually used for an arc of a circle, but kind of the similar meaning. So these angles look at the same side of the quadrilateral AD. So let's prove this. So again, in one direction the proof is simple. So like if it is, so we suppose that it is cyclical. Suppose that ABCD is cyclic. Then, so let's draw another picture. So then we know already that its vertices lie on a circle. ABCD, and these two angles are equal because they're inscribed. So the angles ABD is equal to, so it's an inscribed angle that subtends the arc AD, right? So it's equal to 1/2 of the arc AD. And the same is true for the angle ACD. It subtends it's an inscribed angle that subtends the same arc. So we know that all inscribed angles subtending the same arc, they are all equal between each other. So these two angles are equal. So that's it for the proof in this direction. And in the opposite direction, so again we suppose that these angles are equal. Suppose the angle ABD is equal to the angle ACD, and we can do a similar proof as in the previous in the first theorem. So basically we have a quadrilateral. So these angles are equal. We consider circumcircle of so let's draw it slightly more different. So A, B, C, D. So we consider the circumcircle of the triangle BCD, and let's say that it intersects the diagonal AC at some point A prime. A prime. This is this point. So then we consider this quadrilateral, right? So then the quadrilateral A prime BCD is cyclic by construction, and then the angle A prime BD is equal to let's write it on the separate line. A prime BD is equal to the angle A prime CD, and A prime CD is the same as ACD because A prime is on the diagonal, so this is the same as ACD, right? And so now we look at this equality and at this equality, and we conclude, so on the right side, on the right hand side, we have the same angle, so this angle should be equal to this angle, or we can continue here, like, because of the original condition, right? This should be equal to ABD, so we look ABD. So we look at this and at this. So A prime BD is equal to ABD. So look at the picture. A prime BD is equal to EBD. So from this we immediately conclude that the line, well, like the line A prime, like A prime B is the same line as AB, and from this we conclude that A is equal to A prime because and A prime is the points of intersection of these two lines with the diagonal AC. So since this is the same line, then this is the same point, and from this we get that ABCD is cyclic, which concludes the proof. Yeah, so these are basically the three main criteria that a quadrilateral is cyclic or inscribed. So that's it for this video.